start recording. We're just going to do about 4 problems today, y'all, out of 5.2. Again, the homework is there, but it's not due till next Monday, y'all, because next Monday we'll finish up 5.2, okay? So, I am recording again, y'all. Again, there'll be 2 different videos. I'll upload 5.1 and then I'll upload 5.2. I'll call it 5.2 part 1. And then on Monday we'll do 5.2 part 2. Okay, but the definite integral is 5.2. And we're going to talk about the definition of a definite integral. We're going to explain terms in the integram, limits of integration, variables of integration, explain when a function is integrable, relationship between the definite integral and the net area, and average values of functions. Okay, so it says, if f of x is a function on the interval from a to b, the definite integral of f from a to b is given by, and we have that little integration symbol, from a to b of f of x dx is equal to the limit of, I want you to think about some of these terms here. So n is going to what? N is going to infinity. Does anybody remember what this symbol is here? The sigma, but what does it mean? It means I'm doing what? We're adding, right? So look what we're doing. We're doing an infinite sum, okay? Of f of x to the, or x star with a little I delta x. Okay, so let me explain what this part means. What this part means here, y'all, is if I had a function that looked like this, I'm just going to kind of make it up. Okay. Here's my A, here's my B. We're going to take these little tiny rectangles. These rectangles are going to be really, 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 like I can't emphasize really enough, small, okay? The distance between each of those rectangles is delta x, okay? Remember when we did the area right now, wasn't the width of all of our rectangles the same? So like the width, all of them happen to be 3, or the width, all of them happen to be 6. Okay, so those widths are all going to be the same thing. And then we're finding the heights of each of those rectangles, right? So those heights happen to be the little x I with the little star. What that means is these are the heights of those rectangles. So remember how we find the area of a rectangle? We take the width times the length. That's what that part right there tells us. What we're doing is we're going to add up an infinite number of rectangles. And you're saying, okay, hold on. How can I add up an infinite number of rectangles? That delta x, y'all, is really, really, really small. So those rectangles are almost like, I don't have one here with me, but you know what? I have one in my, So for those of you guys that are watching from home, you can't really see what I'm doing, but what I'm doing is I'm picking up a piece of paper, and I'm trying to find the area of a rectangle that is about that wide, okay? And so, guys, those of you who are watching from home, let me do this just so you guys can see what I'm doing. So let me stop sharing that real quick. Let's go back to the camera. Here we go. I'm trying to find the area of a rectangle that is like as wide as that piece of paper. So that's a pretty narrow rectangle, right? That's in essence what we're doing over here. So let me get rid of that and come back this way. It's exactly what we're doing. We're finding. So y'all, have you ever had those potatoes that are kind of like made like that, scallop potatoes? Like, oh man, that stuff hits so good, doesn't it? Okay, so if you can think about, and I don't know if you've ever seen how they cut them. They have this little machine called a mandolin, and they take potatoes and they do this something. So they're like, they're cutting them super, super, super thin, and that's kind of what we're doing. We have these little rectangles that are like paper thin, right? And they're so thin that we have to add an infinite number of them so that we can find that area. That's what it's going to give me a more accurate model, because the thinner my rectangles are, I'm going to have less of either an overestimate or an underestimate, like when we're doing our areas right now. That's what we call a definite integral. Okay, so look, Yes, go ahead.
What is that? Okay. I know you said that the multiplication people, but what is that X multiplication?
The little star with the eyes?
Yeah.
Okay. Isn't those going to be the heights? So look at the picture up here, John. Those are the heights of each of my rectangles.
Oh,
Because there's so
size
many.
of the star symbol on top?
Yes, that is f evaluated at each of those little intervals, right? Because I'm going to have each of those little tiny intervals here. Okay. Now, so let's take a look, y'all. Let's do the first problem that I have here. And it says, evaluate the definite integral by interpreting in terms of areas. Okay, so the first thing we're going to do here, y'all, we're going to integrate. We're going to integrate this expression right here. Okay, anybody remember what the antiderivative of 3x would be?
Uh,
3 over 2 with an x to what power? To the square, right? Because remember, didn't we say we have to add 1 to the power we already have, and then we got to divide it by that same number? Again, y'all, just to do like a little check, right? So if I was going to go, okay, hold on, let me make sure I'm doing this right. I would have to take the 2 times this, so that would give me a 6x over 2. That's the 3x. Oh, yeah, that's exactly what we have. Okay, so we're just making sure that we did the check right. Okay, and then what is the integral of a minus 15? Negative 15x. Now, guys, on Monday, we always talk about, well, we have this value of c. When we're doing a definite integral, we don't need to worry about the c number. I'm going to explain to you in a minute. What we're going to do now, y'all, is because we have these two numbers here, what those two numbers mean is we're going to evaluate this expression at 7, and then we're going to evaluate it at 3, and then we're going to take the difference. So look, this is what I'm going to do. I'm going to write it like this. I'm going to write 3 times 7 squared over 2 minus 15 times 7 minus 3 times 3 squared over 2 minus 15 times 3. Okay. All right, so let me grab my calculator. Let me see if I can do this part right here. So y'all, again, if I was sitting where you're sitting, my first thing would be, you know what? Let me go to my y equals. Let me clear that out. And I'm going to write in parentheses like this, 3 divided by 2, and then I'm going to put an x squared next to it, okay, and a minus 15x, okay, and that's going to be that's my equation that I have right there, right? So 3 halves x squared, so 3 halves x squared. Guys, I'm putting the 3 halves in parentheses because I don't want it to think about, I don't want my calculator to interpret the x squared is on the bottom. You know what I mean? Like I'm dividing by 2x squared. So that's why I've left my 3 halves in parentheses. Okay, so now I'm going to hit quit here. I'm going to go to my y bars. Y bars right there. I'm going to evaluate this at the first number, which was 7. Okay. All right, so look what I'm coming up with. I'm coming up with negative 31.5. Y'all, I'm going to see, I don't exactly know how they're going to ask you to enter in your answer, but I'll leave it like that. I'll leave it as negative 31.5. Okay, and then I'm going to do the same thing here at 3. And I'm coming up with another negative 31.5. Okay, now notice what I'm doing, y'all. The operation says we're going to subtract the 2. So if I have a negative 31.5 minus another negative 31.5, let's see. Yeah, that's going to give me 0. Okay, now let's take a look here and see if we can't figure out what is happening. Okay, so that's what I'm ending up with right here. Now it says evaluate the definite integral by interpreting it in terms of areas. So let me see, y'all. If I were to think about the original function that I had here, 3x minus 15, okay? So let's see. If this is a negative 15, this should be a positive 5. 3x minus 15. My graph looks something like this here. And you're evaluating this between, what, 3 and 7? So here it is at, that's the number 3, that's the number 7, and I want you to think about, let me get rid of that. I want you to think about what we have here. We have this area and we have that area. Okay, y'all, when the area is above my x-axis, we say the area is positive. When the area is below my x-axis, we say the area is negative. If you notice, those areas are both 31.5, roughly. So if one of them is positive or one of them is negative, wouldn't they cancel each other out? And that's why we ended up with a what? With a 0, okay? But that's all it is I'm really doing. I'm just evaluating this integral. Yo, if I end up with 0, then that's what I end up with. I end up with 0, okay? But that's basically what was happening here. And all I had to do was just integrate this and evaluate it at each of those two numbers and subtract it. Now, you guys, I told you a little while ago that I didn't have to worry about my constant c. And I told you, I want to explain to you, why don't I have to worry about my constant c? I want you to think about this for a second. Suppose I had that constant c here, and I had that constant c here. So I would have 31.5 plus c, and because there was a minus originally right here, minus, and I would have a minus c over here, but I put a plus 3. Wouldn't this positive c and that negative c end up canceling each other out? Because I'm going to subtract them. The constant's going to be here, but then I'm going to have to subtract the constant over here. So that's why we say we never have to worry about that constant of integration when we have what we call, y'all, a definite integral. So when I have those limits of integration, those are what we call limits of integration, I don't have to worry about the plus c. I can just do my integration, evaluate it at the top number, evaluate the bottom number, and then find the difference between those two. Okay. So look, y'all, I'm going to do the same process in the next couple of problems. I only want us to do a couple of problems today, y'all, and then we'll call it a day. So look, this is the next one I want to try to do. Yeah, 0 was my answer. When we integrated it, we ended up with 0. Okay. Now, let's take a look at this one here. It says, to find the blue shaded area above, we would calculate this integral here. And the integral from a to b of f of x dx is equal to the area. Okay, y'all, just to give you a heads up, this is always the a, and that is always the b, okay? The a is always what we call the lower limit, the b is what we call the upper limit. So what would my lower limit here be? 1. And my upper limit would be? Okay. Now, what I need to do is I need to figure out, can I find a function? Can I find an equation, y'all, for that line right there? Okay. Let's think about it this way. Okay. Y'all, remember this formula here? Y equals mx plus b? Okay, so let's do this. Let's find the rate at which the line is decreasing. So I want you to think about this for a second. Let's say from this point here, say from this point to that point, how many spaces do I have to move down? 2. 1, 2, 3, 4 to the right. So would you agree that my slope is negative 2 over 4? I'm going to reduce it in a second, right? Okay. Plus b. Now remember what b is. B is the y-intercept. It's where it hits the y-axis. Where do I hit the y-axis? If this is 4, don't I hit it at 5? Okay. So look, y'all, I'm going to write f of x equals negative 1/2 x plus 5. That is going to be my f of x. So right here, negative 1/2 x plus 5. Okay. Now, y'all, now I want to find the area. So remember how I'm going to find the area. We're going to integrate from 1 to 3 of a negative 1/2 x plus 5 with a dx, okay? Because we're integrating with respect to x. First question, does anybody know what is the integral of, or the antiderivative of negative 1/2 x? Let's see. Okay, what's the power of my x right now? It's a 1. So do you agree it's going to become a 2? Okay. And then we're going to have to divide that number by 2. But look what number I already have in front. I already have a 1/2, don't I? Okay. Plus, what's the integral of 5? 5x. That one we know. Okay, so look, isn't this right here, y'all, going to give me a negative 1 over 4 x squared plus 5x? Again, if you were a little uncertain of yourself, how could you check it? Take the derivative, right? So we would say, look, negative 1/4 times 2. Oh, look, that's negative 1/2 with an x. Oh, yeah, that's what I got right there, right? So that could be how I could check it out real quick. Okay. Now let's keep working. So remember what we're going to do now, y'all. We're going to evaluate this from 1 to 3. Again, y'all, if I'm doing this, like John said, is there a faster way to do some of these things? Yeah, I'd like you to look for faster ways too. So I would probably just enter this in as negative 0.25 x squared plus 5x, because negative 1/4 is the same thing as negative 0.25. And then I would quit this and I would go to my y bars and I would evaluate this first at 3, and I'm coming up with 12.75. And then I would do the same process again, but now I would evaluate it at what number?
1.
At 1, and I'd come up with a 4.75. And remember what I need to do with those two numbers now? We got to subtract them, right? So 12.75 minus 4.75, wouldn't that just give me 8? And there would be my answer.
What is subtraction?
Because that's what I'm doing my, I think it has it up here. That's because those are my limits of integration. I'm finding the area between those two portions. In essence, John, what we're really doing when we're doing that, let me clean this up a little bit. We're finding the area, let me do it with the thick marker here. Okay. We're finding the area like this the first time. And then the second time, we're finding we're finding the area like this. So we want to find the area of just the blue part. Don't I need to take the green minus the red? And that's in essence what happens there. Better? Good, good. Good question, man. Good question. Yeah, no, it's okay. And look, y'all, let me ask you another question. Could we have done the same? Could we have played the same game doing like triangles and all that kind of stuff? Could we have done the rectangle, triangle, even trapezoid type of stuff here? Couldn't we say, look, here is a rectangle, and then here is a trapezoid, and we can find the area like that too? You know what I'm saying? And that's in essence what we would be doing. But we just did it. We did it using calculus, but we could have done it using um, like basic geometry. We could have said, look, let's do the area of the rectangle, let's do the area of the trapezoid, and we should still come up with 8. Okay. The nice thing about this, y'all, doing it this way is we know how to find antiderivatives, we know how to evaluate functions, and so we're not having to do as much of that geometry stuff. But visually, the geometry stuff also makes sense because it lets me know what it is I'm doing. Y'all, this problem here, I'm going to skip it. We'll come back and do it on Monday, okay? It's not necessarily a difficult problem, but I just want to hold off on it on Monday. Okay? Let's do this one because this is a very straightforward type of definite integral problem. Okay? So we're going to go slow. We're going to do this one piece at a time. First question. Does anybody know what is the derivative of a 4x squared?
4x cubed over 3.
Very good. 4x cubed over 3. Plus, what about the derivative of a 3x to the 7th?
3x to the 8th over 8.
Very good. Okay, y'all, we're going to do this evaluating in 2 portions. We're going to evaluate it at 3. We're going to evaluate it at negative 4. We're going to take the difference. Okay, so now I think what we've done so far, y'all, is the hardest part. Because look, my second part now is going to say, look, enter in 4/3. Close my parentheses. X to the 3rd plus parentheses 3 over 8, close my parentheses, x to the 8th, okay, 4/3 x to the 3rd plus 3 over 8 x to the 8th, there it is. Okay. Let me quit that. Let me go to my y bars. I'm going to evaluate this now at 3, and I'm coming up with like 2496.375. Okay. And I'm going to evaluate this again, y'all, but now at a -4. And I'm coming up with a 24,490.667. 490. Yes, 490.66667. We'll go something like that. And now, remember what I'm going to do now, y'all? I'm going to subtract the two. Always the first one minus the second one. Okay, 2496.375 minus my answer that I got earlier. And I'm coming up with a negative 21,994.29167. $29. And y'all, I think, I'm going to try something here. Jennifer was asking about this the other day. If I go to math and I do that fraction, oh man, I didn't do it. Okay, it didn't. Yeah, I mean, we can do it because we know that for the first one, the 2496.375. If I do this math fraction, I'm coming up with 19,971 over 8 minus this one here is going to be like 24, 4, I missed something, 21,000, there we go. 21,900 and, oh, no. What did I do? What was it? 24,490. 67, okay. 24,490 and 2/3. So I can make that into a improper fraction. 24,490 times 3, add it to 2. Okay, so that number over 3. Okay, so let me see, 73,472. Okay, so then you could just subtract this one here minus that one there. And I want to say maybe the calculator will do the fraction for me, you know what I mean? But I would probably enter this in. Again, this is just if you wanted to do that stuff. 71. That's what I wanted to do. Sorry, 19,971 over 8 equals minus 24,4. Yeah, 73,472. And if I do math fraction, does it do it here? Still not doing it.
Well, the fraction would be negative 527,853.
There you go. So you got it. I guess, calculators gonna, even like these calculators, at some point they have limitations, you know what I mean? I don't know if my calculator app would do it or not. I won't mess with it right now. But anywho, this is what I'm coming up with. You know what I mean? Straightforward type problem. Guys, I didn't realize, but we are out of time. So we will stop right there. We will pick up where we left off. So that is it for us today, y'all. We did big work on Wednesday, didn't we? Man, that's not Wednesday work. That should be like Monday work. But anyway, we did big work today, y'all. Let me go ahead and stop